Welcome back, and this is the next in the series of videos looking at intermolecular forces. To understand intermolecular forces, you will have first needed to get to grips with shapes and bond polarity. We generally say that the bonding within a molecule is called intramolecular, but in this topic we're interested in the forces between the molecules, and these are called intermolecular. And you need to be very careful that you're talking about the forces between the molecules, not the forces within the molecule. There are three types of intermolecular forces that you need to be aware of. The first one is London forces. Now these are often called by a variety of different names, including van der Waals forces, dispersion forces, and also instantaneous dipole-induced dipole forces. The next one is permanent dipole. And the last is a special case of permanent dipole forces called hydrogen bonds. These are still intermolecular forces, not full bonds. So the melting point and boiling point of a substance can give us a measurement of the strength of these intermolecular forces. As the higher the melting point or boiling point, the stronger the intermolecular force will be. So when we melt or boil a molecular solid, it's the forces of attraction between the molecules that need to be overcome, not the forces within the molecule. So for example, when we boil water, we don't break the strong covalent bonds between the oxygen and the hydrogen. Rather, we overcome the weak intermolecular forces between the water molecules. Of the molecules in the table, we can say that ammonia has some of the highest or the strongest intermolecular forces. Why? Because it requires the most energy per mole to melt. Whereas on the other hand, the methane is one of the lowest, as it requires the least amount of energy to melt or to vaporize. Another molecule with strong intermolecular forces would be ethanol, as it has again a relatively high molar enthalpy of melting and molar enthalpy of vaporization. The first type of intermolecular force we're going to consider are the London forces. All molecules possess London forces, as these London forces are determined by two factors: the number of electrons, and as all my molecules have electrons in them, they're always going to have London forces, and also the shape of the molecule. London forces are caused by an instantaneous induced dipole force, which is why they're often called instantaneous induced dipole. If you consider a molecule, such as a hydrogen molecule, with an electron in it, or electrons in it, those electrons are constantly in motion all over the molecule. At any one point, that electron might be up one end of the molecule, in which case this end temporarily becomes delta negative, and this end becomes temporarily delta positive. This is what we call an instantaneous dipole. It's not a permanent feature because the next second, or even nanosecond or femtosecond, the electron could be over the other side. But it is at that particular moment in time a dipole, and this is why it's called an instantaneous dipole. This can then induce a dipole in an adjacent molecule, and this is why we call it the induced dipole. And there is a force of attraction between these two molecules. Now, if the molecules are moving slowly enough, in other words, they have a low enough kinetic energy, those forces of attraction can make the molecules form a solid structure. So this random movement of electrons gives rise to an instantaneous or temporary dipole. This induces the dipole on the adjacent molecule, and you get this force of attraction. Please remember that these are not permanent. They appear and disappear all the time, but if the molecules are moving slowly enough, they can actually get themselves into an ordered arrangement in a solid. The two things that the strength of the London forces depend upon are the number of electrons. The more electrons, the stronger the London force is, and also the shape of the molecule. Long, thin molecules which can pack more efficiently and get closer together have larger instantaneous dipoles. If the molecules are not able to pack efficiently, their points of contact are much lower and the intermolecular forces are weaker. If you remember back to your alkanes notes, we drew this graph and we said that as the number of carbons increased, the temperature or the boiling point also increased. Now we can understand why this is. Well, as we're adding carbon atoms, we're also adding electrons. So more electrons equals stronger London forces. Therefore, more energy needed to overcome them. So it's the same 3 marks each time. You've got more electrons. More electrons gives you stronger London forces. The stronger London forces mean that you will need more energy to overcome them. So on the next page, we've drawn pentane, 2-methylbutane, and 2,2-dimethylpropane. What you should notice is these are isomers. In other words, they have the same number of carbons and hydrogens, but they have a different carbon skeleton. So they're called structural isomers. In each case, because they are isomers, the number of electrons in each of them is the same. So the difference in the boiling point can't be down to the number of electrons. It has to be down to the shape. So in all 3 cases, we have the same number of electrons. However, the 2,2-dimethylpropane has several branches on it. And those branches stick out and make it difficult for the molecules to pack efficiently together. We say it reduces the points of contact. Because those points of contact have been reduced, because it cannot pack efficiently, the London forces themselves are weaker. Therefore, we require less energy to overcome, and the 2,2-dimethylpropane has a lower boiling point. We can also use this idea to explain the change in the boiling point of the group 7, the halogens, as you go down the group. Group 7 is an unusual group because it goes from gases at the top to solids at the bottom. It's one of the very few groups that will do that. So fluorine and chlorine are both gases at room temperature and pressure, whereas bromine is one of the few elements which is liquid and iodine is a solid. Again, the reason they change their boiling points as you go down the group is due to the increase in the strength of the London forces. So it's the same 3 points again. As you go down the group, the number of electrons increases. Because the number of electrons increases, the London forces are going to get stronger. Because the London forces are stronger, you're going to need more energy to separate the molecules from each other. Do notice we're not talking about the bonding within the molecule, only the forces of attraction between the molecules.